When we look up at the night sky, we see thousands of stars shining brightly. In fact, there are billions upon billions of stars stretching across the universe. But it wasn't always this way. Once there was a time when there were no stars. There was nothing to light up the sky. This time of darkness was just after the Big Bang, 14 billion years ago.
The universe started off as a hot fireball, and it cooled down, and after about 500,000 years, our universe entered a literal dark age. The universe then stayed dark until the first stars formed and lit it up again.
Lost inside this cosmic dark age is one of the great mysteries of science. The very first stars, the creators of everything. Stars are the factories of the universe. Inside their burning cores, all the elements that make up everything we see and touch today are created. But without those very first stars to begin this process of creation, there would be no galaxies, no Earth, no us. The great puzzle at the heart of this creation story is, if the stars create everything, then how were the very first stars themselves created, all those billions of years ago? It is a mystery that has baffled scientists for generations.
A very difficult question is trying to work out how those early stars formed. It's a very difficult theoretical question because we don't have observations to guide us.
There are no observations because there is not enough light to see back into the cosmic dark age when it all began. And light is what astronomers need to see back in time. Sunlight takes 8 minutes to travel to Earth. When we look up at the sun, we see it as it was 8 minutes ago. And when we see the light from other stars from further away, we are in fact seeing further and further back in time. So, when we look at a star from the other side of our galaxy, 100,000 light years away, we're really seeing it as it was when the light left it 100,000 years ago.
As we look out across the universe at the most distant objects that we can see, we're actually going backwards in time, looking backwards in time, billions of years.
But no matter how hard we look, no one has been able to see back to the cosmic dark age until now. And solve the mystery of how the very first stars were made. Something that sent science on a quest that would span the entire universe.
Who would have thought that this journey would take us to the edges of the universe, the biggest explosions in nature, black hole birth, star death, just the most exotic phenomena that I've ever seen, and I've been studying explosions all my life.
The journey began over half a century ago with a bizarre chain of events at the height of the Cold War.
Attention all bases, attention all bases. This is Iron Hand, this is Iron Hand. This is a shock alert. I repeat, this is a shock alert.
It was the 1950s and the world was gripped by fear. The Americans were convinced the Russians were trying to develop nuclear weapons behind their back. And because they thought the communists so devious, they decided that the most likely testing site for these new weapons was not in the oceans, not in the deserts, in fact, not even on Earth itself. The Americans believed the Soviets were testing nuclear bombs on the dark side of the moon.
I mean, come on, give me a break type of thing nowadays, the ridiculousness of it. But the Soviets would buy into the same paranoia because their paranoia was, you know, might say more deeply inbred.
Sterling Colgate was an expert in nuclear bomb testing. He was put in charge of designing a series of satellites sensitive enough to pick up even the faintest trace of a nuclear explosion from as far away as the moon.
So the satellites were made to detect nuclear violators, cheaters, which meant they had to be a great deal more sensitive than any sensible bomb physicist would have ever said they needed to be.
Colgate's satellite was designed to pick up the one telltale sign of a nuclear explosion that not even the Russians could hide. Gamma rays, the deadliest form of energy in the universe. Colgate's satellite was launched amidst great secrecy. But what it would discover would turn out to be far more deadly than a Russian nuclear bomb. On the 2nd of July, 1967, it seemed their worst nightmare had come true. Colgate's satellite picked up a huge burst of gamma rays.
A nuclear bomb signal that you'd expect to see from a test in space of a nuclear weapon would be first a pulse, smaller pulse, and then followed by some time a much bigger pulse. And these two pulses are the primary and the secondary.
But the telltale signal was not from any nuclear bomb. It was from something far, far bigger. Something of incomprehensible size.
I was blown away, totally, completely blown away. My God, what the hell are they seeing out there?
And the signals just kept on coming. Something out there was causing huge explosions, blasting out deadly gamma rays.
No one really knew quite what to make of it, and there were preposterous ideas bandied around for a while that even these were interstellar Star Wars going on, and we were seeing the phaser blasts that missed their target, or that comets were annihilating with anti-comets, or little black holes were evaporating. People didn't quite know what to make of it.
Exploding star. But to be sure, they turned to no less an authority than Einstein, and to one of the most fundamental of all the laws of physics. E equals mc squared. This famous equation underpins many of our assumptions about how the universe works. It puts a limit on the size of any explosion. Nothing can explode with more energy than is contained in its mass. So, if some kind of star really was the source of these gamma-ray bursts, then E equals mc squared would tell you how big the explosions could be.
The amount of power you can get from a star is limited according to Einstein's famous formula E equals mc squared. And if we know m, the mass, which we do know for stars, then we know the maximum amount of energy which we could get by any conceivable process.
Once they knew there was a finite size to the explosions, they could then work out how far away they were. When they plugged in the numbers, they realized that these explosions must be happening in our very own galaxy. Any further away, and E equals mc squared would be broken. The explosions would be bigger than was physically possible for any star to produce. And so they scoured the galaxy to find out what kind of star could be causing these bursts of gamma rays. And before long, they thought they'd found the culprit. Neutron stars are amongst the most powerful objects in our galaxy. They are so dense that they have a gravitational pull of such strength that if anything strays too close, it is dragged onto the star with extreme force.
A neutron star is typically just a few miles across and will have a mass as great as the sun. So the densities are just enormous. If you dropped a marshmallow onto a neutron star, it would have the energy of an atomic bomb because the gravity is so powerful.
Neutron stars seemed to contain enough energy to produce these gamma ray bursts. The only question was, what was actually triggering them?
There were a number of ideas relating to neutron stars specifically. The idea was you drop something onto the neutron star and it releases a lot of energy. One idea was an asteroid falling onto a neutron star.
It soon became the accepted theory that neutron stars fired off these bursts of gamma rays if something collided with them. The mystery seemed to be solved. Now they had the answer. Everyone began to speculate about the possible impact of these bursts on Earth. It began to dawn on them that if these explosions were coming from our own galaxy, in effect, they were occurring right next door to us.
If a burst did go off in our own galaxy, it would be quite spectacular. It would be extremely bright anywhere in the galaxy. And if it were close enough, I suppose it could do quite a bit of damage. Some people have hypothesized that major extinctions are the result of gamma ray bursts in our own galaxy.
While they worked out that the odds of Earth being hit again were extremely remote, if it did happen, the effects would be devastating.
Suddenly there would be a light in the sky, if it was 300 light years away, 1,000,000 times brighter than the sun. This would be the equivalent of 1,000,000 megaton bombs going off all over the Earth at the same time. It would be Hiroshima all over the world.
Bohdan Paczynski was an astronomer more interested in facts than the complex theories of the time. He decided to concentrate only on what he could actually see, the direction the bursts were coming from, and their distribution across the sky.
When I looked at gamma ray bursts, I realized, at least for me, it was hopelessly complicated. So I gave up on that instantly. I just thought it's far too difficult for me. And instead I looked at things, aspects of gamma ray bursts which were easy to comprehend. And these are the distribution properties.
To plot the direction of the bursts, Paczynski turned to our galaxy, the Milky Way. When we look up at the night sky, we see the Milky Way as a narrow streak of stars. Astronomers call this area of the sky the galactic plane. But ours is a distorted view because we sit at the very edge of the galaxy. In fact, our galaxy stretches for 100,000 light years across space in a flat disk. If these bursts really were coming from within our galaxy, then Paczynski realized they should all be coming from just one place.
If gamma ray bursts were in our galaxy, they should be distributed the way everything is distributed in our galaxy, which means they should be near the galactic plane and possibly also concentrated towards the galactic center.
But when he pieced all the available data together, what Paczynski saw was something quite unexpected.
Gamma ray bursts were coming to us from all over the sky with no particular relation to our galactic plane or the galactic center. And in fact, that is what I saw in the data.
So the gamma ray bursts were not coming from the area of the Milky Way. They were coming from all over the night sky. To Paczynski, this could only mean one thing.
Contrary to popular belief, gamma ray bursts could not possibly be in our galaxy, but instead they should be very, very far away, sort of at the edge of the universe.
Paczynski had thrown down a challenge. The neutron star theory, he declared, was wrong. The explosions had to be coming from something far bigger and far further away. The problem was that Paczynski's observations seemed to require explosions with more energy than any star had ever produced.
If you took a model that would work at the distances Baudin was describing, you would have to convert 1 million Earth masses into pure energy instantaneously. Well, within 10 seconds anyway, and in the form of gamma rays, and get it out, and get it 3 billion light years to us. And so, yeah, okay, Baudin, maybe, but be good. Work on something else for a while.
In 1991, NASA launched the BeppoSAX satellite. Equipped with state-of-the-art detectors, it was going to study the bursts in detail for the first time. But as the data came in, a disturbing picture began to emerge. What they'd expected was that the bursts would line up with the galactic plane, meaning they were coming from within our own galaxy.
The first dozen or so gamma ray bursts weren't lining up with the galaxy. The next dozen or so also weren't lining up with the galaxy, but they happened to be randomly distributed throughout the sky.
There was now no doubt. Paczynski had been right all along. But Paczynski's triumph threatened to plunge science into chaos. If the bursts were coming from beyond our galaxy, then they had to be caused by something far bigger than science could explain.
If they were really coming from distant galaxies, it was a phenomenon unlike anything we've seen before. The amount of energy release, the rate of energy release was greater than anyone had ever seen before in any other form. And the details of how you got that, nobody could understand how that could be. It was pressing the limits of our understanding.
It was now clear that these explosions were of an almost inconceivable size. So big, in fact, that they might even be violating Einstein's fundamental law, E equals mc squared. And that was meant to be impossible. It now became imperative to get an accurate distance measurement of the gamma ray bursts. Scientists turned to the only technique they had for precisely measuring how far away objects are from Earth. A technique called redshift.
Redshift.
Redshift is a fantastically important tool for astronomy. Basically, measuring the redshift to an object is what tells us the distance of that object in astronomy. And the distances that we're talking about are so vast that they're extremely hard to measure by any other way, but redshift actually turns out to be quite straightforward.
Most explosions cause a flash of visible light. Scientists can split this light into its spectrum of colors. The further away an object is from Earth, the more red the light looks. The problem with gamma-ray bursts is that they produce no visible light, so they cannot be redshifted.
Even today, we cannot focus gamma rays. There are no lenses that will make an image in gamma rays.
But then they realized that when the gamma rays blasted out, they would pass through all the gas and dust floating in space. This material would be heated up and would glow. This afterglow would be visible and might last for several days. If they could find it, it could be redshifted.
If we could ever find just one glowing ember of a gamma ray burst, the mystery would be cracked open, because we'd have a location and we could go look with the full panoply of radio telescopes and telescopes in space and big telescopes on the ground.
The hunt was now on for the afterglow. On the 9th of May 1997, a very bright gamma-ray burst was picked up. All over the world, telescopes were being reprogrammed and refocused in the hope of catching this elusive afterglow. And then it happened. A faint flash of light was spotted. The astronomers analyzed the light. It wasn't at the blue end of the spectrum, suggesting the burst was from inside our galaxy. The light wasn't even green. The yellow would have indicated that the bursts were coming from far outside our galaxy, but it wasn't there either. This light was so far towards the red end of the spectrum that the burst could only have come from further away than anyone ever imagined.
Redshifts proved conclusively, beyond any doubt, that they were coming from the edge of the universe and nowhere nearby.
So the gamma-ray bursts were coming from the other side of the universe, 10 billion light-years away. No star could be big enough to produce that amount of energy.
If you took all of the stars and all of the galaxies and all of the quasars and everything in the universe and put them all together at one point at the distance of a gamma-ray burst, it would not be as bright as the gamma-ray burst.
It meant that they were being produced by explosions that didn't just test Einstein's law to its limits. They completely shattered it.
The amount of power involved to produce a bright flash detectable literally 10 billion light years away was a remarkable source of energy and remarkable phenomenon that we really had to try and explain.
Scientists were stunned. Now they were confronted with something that was physically impossible.
What was mind-boggling was how that much energy is converted into gamma rays. Because the amount of energy was so large that people felt, my goodness, maybe new physics is required.
For a brief moment, it seemed that E = mc squared was wrong. And if a law as fundamental as that was wrong, then perhaps everything we understood about the universe could also be wrong. Someone had to restore order. The man who came to the rescue was one of astronomy's heaviest guns. Martin Rees is nothing less than the Astronomer Royal.
Physicists always like to observe places where the laws of nature are, as it were, being tested to breaking point, because then we will see how robust those laws are, perhaps discover something new. And the most exciting parts of the universe, from the point of view of a physicist, are the places where the most extreme conditions prevail. And I think there's a clear consensus that the gamma ray bursts involve the most extreme physics we know about.
Rees realized scientists had always made one assumption when calculating the size of the bursts. Explosions normally spray out energy in all directions. So scientists had assumed that what we saw on Earth was just a tiny fraction of the overall energy produced by the explosion. And there lay the problem.
If they really were emitting energy over the whole sky, not just in direction toward us, would involve so much energy that that would violate Einstein's E equals mc squared.
But Rees is an expert in the most bizarre objects in the universe: black holes. A black hole is created when a star burns up all its fuel and dies, collapsing in on itself. They have such immense gravity that they swallow up everything around them. And as they do, they throw out pure energy in two powerful jets. Rees believed that the same process was at work with the gamma ray bursts.
If it were the case that the gamma ray burst energy is coming out not in all directions around the explosion, but is channeled in a particular narrow beam or jet, then it means that the total amount of power coming from a single object is less than it would be if it had to radiate over the whole sky, because there'd be a sort of searchlight beam coming towards us.
It would mean the energy we were detecting on Earth would be almost the total energy produced by the explosion.
It doesn't take nearly as much energy if you can shoot the light down a gun barrel and shoot it right at the observer. Then you don't have to waste energy in other directions. We call this beaming.
Using Rees's theory, they recalculated the size of the explosions and found they were now well within Einstein's limit. There was a way gamma ray bursts could come from the furthest edges of the universe and still not break the fundamental laws of physics. But Rees's theory did something else. It gave scientists the first clue to what might actually be causing these mysterious explosions. It had to be something to do with stars dying and the black holes they then create. What no one could have guessed was that the true wonder of these gamma ray bursts was yet to emerge.
Working in this field has really been a roller coaster ride, you know, thinking you understood something and then realizing you're completely wrong, and then having it turn out to be, for me, one of the most exciting phenomena in the universe.
It would be a phenomenon that could allow science to reach back to the cosmic dark age itself. began on the 22nd of February 2001. Telescopes around the world picked up the second most powerful gamma-ray burst ever detected. Data started pouring into the Very Large Array in New Mexico, the world's largest collection of radio telescopes. In charge was Dale Frail.
After one of these bursts goes off, there's a mad frenzy of phone calls around the world trying to capture the burst. The earliest evolution of these events is very important to us as astronomers, so that we get on the phone to grab as many resources as we can around the world while the source is rising. And in this particular event, we were able to get on within a few hours of the event.
As Frail analyzed the pattern of radio waves that accompanied the burst, something struck him. Usually, in an explosion, the energy blasts out, reaches a peak, then fades to nothing. But that's not what Frail saw.
What we'd expected to see is something rising, reaching a maximum, and then fading away with time. But to our complete surprise, what we found was a signal much stronger than we expected to see, and it stayed constant during the entire time we observed it. In fact, it stayed constant as far as we know up to this day.
Frail couldn't figure out how an explosion could give off a constant stream of energy long after it should have disappeared. And then he realized he wasn't just looking at an explosion, but at one of the wonders of the universe. There is only one type of place known to emit a constant radio signal like the one Frail had seen. Star nurseries. The places where new stars are born.
They are stellar nurseries where new stars are being born on a daily basis. Brand new stars every day.
Star nurseries are found in all galaxies. They are one of the most extraordinary things in the universe. They consist of huge clouds of gas and dust, hundreds of light years wide. Inside these clouds, the pressure is so great in places that hot, dense clumps form. These get so hot that a nuclear chain reaction starts and the clump of gas ignites, becoming a star. It was these star nurseries that seemed to be producing the gamma-ray bursts.
The detection of a gamma-ray burst inside one of these stellar nurseries points inevitably to the idea that gamma-ray bursts are somehow connected to this process of star forming.
This just didn't make sense. The theory was that the gamma-ray bursts were caused by black holes, the result of stars dying. So why were they coming from the places where stars were being born? The person who was to bring life and death together was Stan Woosley, a man long obsessed with things that go bang.
I've always loved explosions. I loved fireworks. I loved to put together chemicals of different kinds that you can't get anymore and make little bangs when I was a kid, safely away from people. And the idea that the gamma-ray bursts turn out to be just the biggest bangs in the universe is just a real thrill.
Woosley's aim was to work out how a star could die while still in a star nursery. Most stars live for around 10 billion years. Only then, long after the nursery has disappeared, do they die. But Woosley worked out that if a star was to grow to an enormous size, what he called a massive star, then the whole cycle of life and death would be accelerated. A massive star would burn up all its fuel so quickly that it would live just a fraction of a star's normal life.
Now, a star that has 10 or 20 times the mass of the Sun will have a much shorter life. It has more mass to burn, but it burns its fuel very rapidly. It's the fast livers of the stellar lane.
It means these massive stars would die while they were still very young, still inside the star nurseries.
These big stars die very close to where they were born. And this means that if gamma ray bursts are coming from massive stars, as we suspect, gamma ray bursts, which are the deaths of these stars, should also be occurring in regions where stars are being born. So this is a clue about what makes the gamma ray burst, the prediction.
Using his theory about massive stars, Woosley put all the pieces of the jigsaw together, and he came up with a theory that explained everything. It was given the name hypernova. It all begins inside a star nursery with the formation of a massive star. The star then burns furiously, using up all the fuel in its core in just 1 million years. It then collapses in on itself, becoming so dense, a black hole is formed. It sucks in all the matter that once made up the star. Out of the black hole burst the gamma ray jets. A hypernova is formed, releasing gamma rays in 2 tightly focused beams. It means that every time we see a gamma ray burst, we are witnessing the death cry of a massive star and the birth of a black hole. The mystery of the gamma ray burst was solved.
Gamma ray bursts are the most extreme objects we so far discovered in the universe. They involve more power, more intense radiation than we found anywhere else. They probably are the places where black holes are newly forming.
But now it seems there's one final twist to this story.
The gamma ray bursts were astounding when we first discovered them. They've become even more astounding that we know how far away they are. And now they're opening up a new window to the distant universe.
Some now think that the gamma ray bursts may solve the problem that has defeated scientists for so long. What happened in the cosmic dark age?
One of the big challenges of observational cosmology at the moment is to try and push our observations as far as we can into that dark age period to see really when the very first objects like stars and galaxies formed.
The reason why scientists are so desperate to find out how those first stars were formed is because they hold the key to the big mystery of creation. Scientists knew that all the elements that make up the universe, the galaxies, the planets, even the air we breathe and the bones in our bodies, were all first made inside stars.
Everything, including the elements that you and I are made out of, has been made as a product of stellar evolution.
This is how the heavier elements are formed. So the iron in your blood came from the center of a star. We really are stardust.
Without stars to make all the elements, there would be nothing. Because when stars die, they explode and scatter their stardust across space. It then becomes a crucial part of the dust and gas that form the next generation of stars. But the mystery is, if the stars make all the elements, then what made the very first stars? The answer has to lie in those cosmic dark ages at the dawn of time. What scientists have now realized is that the gamma-ray bursts may be a way of seeing into those dark ages. We now know these explosions happened billions of light years from Earth. That also means they happened billions of years ago. It has taken all that time for the light to reach us. Scientists now hope that the beams of gamma rays will act like a torch that will guide their telescopes through the darkness. They know that the bursts are guiding them directly to star nurseries. The hope is that they may one day find bursts from the very first star nurseries, where the very first stars were made.
The first gamma ray bursts may be connected with the very first stars, and if so, they allow us to probe what happens in the stage of the universe when it's just coming out of its dark age, as it were.
No one has yet seen a gamma-ray burst from the Dark Age. The oldest we have is from 10 billion years ago, but earlier ones must exist. It's now just a matter of finding them. And then, when we do, finally, we will learn how the universe, as we see it today, came to be.